Hello, my name is John Runciman. I work in the Drilling and Completions Department of C-FER Technologies, an applied research institute based in Alberta, Canada. I will be presenting on the summary of steps required to certify in-situ oil sands processing equipment, which was prepared for the Korea Institute of Civil Engineering and Building Technology. First, I will provide an overview of the project, its objectives, and the Alberta Oil Sands. I will then highlight commercial in-situ recovery processes utilized, as well as the commercial steam generation equipment and its associated challenges. We will then explore emerging steam generation technologies, as well as the methods used to process and recycle produced water. We will then examine well pad separation equipment and equipment certification processes, followed by the project conclusion and question period. Project overview. The focus of this project is to summarize the equipment used in steam generation, de-oiling, and well pad separation systems in Alberta. Note that manufacturers of steam generation and de-oiling technology are identified in the final report, but will not be discussed in this presentation. Another focus of the project was the identification of current challenges facing commercial steam generation equipment and emerging technologies, as well as a review of Canadian equipment certification processes. The information presented is based on industry experts' experiences and publicly available sources. The industry experts contacted were Falcon Energy Consulting Services, who provided a detailed listing of commercial and emerging central processing facility technologies, capital and operating expenditure data, regulatory application information, and relevant design standards. The second industry experts contacted was Ray Engineering and Inspection. These were subject matter experts with experience in the inspection and certification of equipment arriving or located in Canada. Alberta Oil Sands constitute the third largest proven reserves in the world and are located in northern Alberta within the Athabasca, Cold Lake, and Peace River areas. 80% of the recoverable bitumen reserves in Alberta are too deep to be mined and processed from the surface, and as a result require the use of in-situ recovery methods using drilled wells. The most common in-situ production methods involve the use of steam, which is pumped into the reservoir, which lowers the viscosity of the bitumen, increasing the mobility of the oil so it can be extracted. Oil sands production is overseen by the Alberta Energy Regulator, the AER, which is responsible for defining and legislating oil sands projects for the purposes of public and environmental safety, as well as taxation. Commercial in-situ technologies include steam flooding, cyclic steam simulation, and steam-assisted gravity drainage. In steam flooding, steam is injected in a series of wells. A separate series of production wells decreases localized reservoir pressure, and the resulting differential pressure allows the heated bitumen to flow through the formation to the production well. Cyclic steam stimulation is a single well process that involves 3 repeating phases of steam injection, a soaking time, and then production. In steam-assisted gravity drainage, or SAGD, 2 horizontal wells are drilled parallel to each other. Steam is injected in the well closer to surface, and heated oil mobilizes to the bottom producing well. In-situ oil recovery requires significant infrastructure to produce the steam, separate the produced oil from water, and then treat the produced water separated from the oil for the purposes of reuse in accordance with AER regulations. For example, operators must target a 90% recycling rate of injected water. As a result of these significant infrastructure requirements, it has traditionally been uneconomical to build a separate processing facility at each well pad. Therefore, operators compile all necessary equipment in a central processing facility, as detailed in the figure to the right. The most common method of producing steam for in-situ operations is using boilers, which combust fuel, typically natural gas, to heat water passing through tubes or tanks. The most common types of boilers utilized in central processing facilities are once-through steam generators, advanced gas turbine once-through steam generators, and drum boilers. Once-through steam generators are the most common boiler technology used for in-situ central processing facilities, with 170 to 200 installations currently in Western Canada. And their popularity is owing to their ability to utilize suboptimal feed water, which is achieved by operating with much lower heat flux rates than conventional boilers, The steam quality output is approximately 80%, and increasing steam quality would result in solids precipitation, leading to deposition in boiler tubes that requires increased maintenance to mitigate. A steam separator is employed after the once-through steam generator to direct high-quality steam to the injector wells. A portion of the remaining liquid water is recycled back into the boiler, and the remaining water contains solid waste, and that is removed and disposed of as required. Gas turbine once-through steam generator technology utilizes a cogeneration process to efficiently produce both steam and electricity. Natural gas is first burned in a gas turbine to generate electricity, and then the hot exhaust gases from the turbine are passed through a heat recovery steam generator, which uses the waste heat to create steam. Most facilities also employ duct firing in the heat recovery steam generator to generate additional steam, which is then added to the once-through steam generator output, as imaged on the right. In the drum boiler, water is heated within and between two connected drums, a mud drum located at the bottom and a steam drum located at the top. In the steam drum, the steam separates from the liquid water and is extracted, and in the mud drum, solids are allowed to separate from the water. The drum boiler technology has the following advantages in comparison to once-through steam generators, in that it provides high-quality steam, therefore eliminating the need for a steam separator and the need to recycle feed water. And it has a high heat flux to the boiler walls, which allows for a smaller overall boiler footprints. As well, the mud drum allows solids to separate, which reduces the volume of wastewater. The main disadvantage of this technology is the requirement for high-quality feed water to prevent rapid deposition of solids in the mud drum. A drum boiler is typically installed also with an expensive evaporator water treatment system, which will be discussed later. And another disadvantage is that a drum boiler cannot be cleaned with conventional, less expensive once-through steam generator methods, such as pigging. It must be cleaned by personnel accessing the drum. Challenges of commercial steam generation equipment, and the primary challenge is sourcing and treating feed water for the boilers. A large portion of feed water comes from recycled, treated, and produced water, in which the total dissolved solids content increases due to continual recycling. Feed water is often augmented with makeup water drawn from saline aquifers, or, to a lesser extent, surface waters such as rivers, which can vary significantly in total dissolved solids content based on the source or time of year. For example, rivers have a higher total dissolved solids contents in spring when water levels are higher. Another issue facing steam generation technology is the fouling and scaling of the boilers and tubes by unremoved oil, hardness, silica, and other materials, which results in lower efficiencies and can cause damage to the equipment by causing overheating of the tubes. As a result of fouling, regular cleaning of boiler tubes is required, which leads to downtime and additional costs. Environmental challenges associated with steam generation include the associated air emissions, such as greenhouse gas production, which are taxed by the government of Alberta. Achieving more fuel-efficient and electricity-efficient steam generation is desirable, but technologies which provide efficiencies present new challenges, such as drum boilers requiring higher quality feed water. Emerging steam generation technologies which aim to address the commercial challenges listed above include dual-loop systems, direct contact steam generators, air-fired, direct contact steam generators, oxygen-fired, as well as flash steam generators, plasma steam generators, and forced circulation oil sands steam generators. In a dual-loop system, a heat exchanger is utilized to achieve boiling of the feed water. Fluid in a primary closed loop is heated to high temperatures via combustion and is heat exchanged with the feed water under moderate heat flux conditions to generate steam for injection. Fouling rates are greatly reduced as less steam is generated compared to a boiler. And the primary advantage is the potential to use produced water directly from a free water knockout vessel, which is used to separate produced oil, water, and gas, and that bypasses the need for extensive additional water treatment during recycling. The main disadvantage of a dual-loop system is that it requires approximately double the heat transfer area, resulting in a larger footprint than a traditional boiler, and it requires additional pumping power to drive the primary loop. The steam quality produced is as low as 20%, which increases the amount of pumping equipment required to achieve the desired steam flow rate. In a direct contact steam generator, air-fired, feed water is injected directly into a combustion chamber that uses a fuel-air mixture compressed to the produced steam pressure. The process steam leaving the combustion chamber contains steam generated from the feed water, as well as steam generated from the combustion process and non-condensable gases. Unlike conventional boiler technologies, these systems do not transfer heat through boiler walls or tubes, which significantly reduces surface fouling. This allows the use of low-quality feed water, resulting in cost-effective feed water treatment. Steam quality can be increased by operating at superheated conditions, which maximizes steam quality and allows for the solids in the feed water to leave as dry solids, thereby reducing wastewater handling, but introducing a solid waste stream that must be disposed of. The requirement to compress the air and fuel up to system pressure results in additional equipment and expenses, such as a compressor. In the direct contact steam generator, oxygen-fired variant, pure oxygen is utilized in the combustion chamber as opposed to compressed air, and this oxygen is either in compressed gaseous form, requiring upstream air separation, or from a liquid supply. The use of pure oxygen results in more complete combustion, resulting in higher temperatures and steam quality. For example, supercritical steam can be achieved. The only major constituents in the products leaving the combustion chamber are steam and CO2. As a result, the direct contact steam generator oxygen-fired systems are well suited for carbon dioxide capture. These systems are more compact than traditional once-through-steam generators and direct contact steam generator air systems, to the point that it may be considered for use at pad sites. Disadvantages include, though, the requirements for more exotic materials given the hotter combustion temperatures, and the costs associated with pure oxygen separation, purchasing, transportation, and storage. In a flash steam generator technology, a combustion of heating and pressure drop to create the steam. Flash steam generator technology utilizes a combination of heating and pressure drop to create steam. Feed water is first highly pressurized and then heated to a few degrees below boiling point, the saturation temperature, through a series of heat exchangers and an economizer. Steam is then generated by depressurizing or flashing the heated water through an opening in the flash vessel. Plasma-fired steam generators produce steam by heating feed water entirely using plasma arcs between electrodes powered by a high current, low voltage, alternating current, or direct current source. As steam generation occurs within a tank containing mostly water, relatively untreated feed water can be used, reducing treating capital costs. However, as a system is powered by electricity, the operating costs are higher than with traditional boilers. This is a new technology that requires further testing before commercialization. In forced circulation oil sands steam generators, it utilizes a hybrid design that operates like a drum boiler, but can be cleaned using conventional once-through-steam generation techniques such as pigging. Steam and water are separated in a steam drum, with heating occurring in evaporator coils that are placed in a separate furnace. Water is circulated from the steam drum to the evaporator coils, where approximately 20% of the water is converted to steam during normal operation. The steam and water mixture returns to the drum and are then separated, with the remaining water recirculated. Operating with 80% water content in the evaporator coils reduces fouling in the tubes compared to once-through steam generators. The operating temperature of the tube wall is reduced compared to once-through steam generators, which is anticipated to reduce the relative occurrence of overheating failures. The forced circulation oil sands steam generator is designed to handle water quality upsets, as the steam to water ratio can be adjusted using the recirculation pumps when substandard feed water is supplied. I'll now give an overview of produced water processing and recycling. Water that is produced with oil typically consists of free water, suspended water and solids, water and oil emulsions, and/or oil and water reverse emulsions. Water treatment begins at the well pad site with sand and solids removal. Typically, the produced water is a combination of slightly saline formation water and condensed steam that is kept in an emulsion, or at least a high water cut, to facilitate pipeline transportation from well pads to the central processing facility. Water compositions vary from operation to operation, depending on the source of the makeup water, treatment processes used, and reservoir mineralogy or geochemistry. Water management plans aim at minimizing the amount of additional makeup and disposal water through treatment and reutilization to meet regulations and mitigate potential supply scarcities. For example, early SAGD operator plans target up to 95% recycling, and regulations typically call for greater than 90% recycling rates. Water treatment at the central processing facility consists of de-oiling, which is the separation of the produced water from oil, and polishing, the removal of minerals, also known as hardness, silica, and organics prior to reuse as boiler feed water. This can be achieved using a warm lime softening or evaporator process. In the de-oiling stage, the first step in bulk oil water separation occurs in the primary production separation systems, which typically consists of a free water knockout vessel, which is a 2 or 3 phase gravity separator. Free oil and water are mostly separated at this stage. However, oil and water emulsions and suspended solids are too small to be effectively separated by the gravity process utilized by free water knockout vessels. A second oil removal unit process is installed, which includes a skim tank, a gravity separation vessel, an induced gas flotation process, in which injected gas bubbles adhere to suspended matters and float to the surface, and oil removal filters. The de-oiled water is then stored in a produced water tank. The commonly employed treatment system to remove the contaminants remaining after secondary separation is the warm lime softening process. This involves pretreatment of the water with heated lime to reduce hardness and alkalinity, and magnesium oxide to remove silica. The final step involves a series of weak acid cation exchangers to remove calcium, magnesium, iron, and traces of oil. However, fouling organics are not eliminated at that stage. The most common approach to remove these fouling organics in the boiler feed water involves the use of chemicals such as solvents, dispersants or solvents, coagulants, and de-emulsifying compounds. A second method for removing fouling organics is using an evaporator, which evaporates the water and leaves behind the fouling organics. A third method to eliminate total organic carbon is to inject an oxidizing agent such as air, oxygen, ozone, alkali permanganate, chlorine dioxide, or hydrogen peroxide, which chemically reacts with the fouling organics and results in a product that can be separated using filters. Another process to prepare boiler feed water is using an evaporator, which is often installed upstream of a drum boiler to meet this type of boiler's more stringent feed water quality specifications. First, the pH of the produced water is controlled to prevent excessive acidity, which could damage equipment, and then the water is de-aerated to minimize corrosion. The water is then fed into a vertical tube, falling film type evaporator, which allows for the extraction of distilled water vapor that is clear of impurities. The impurities fall into liquid water at the base of the evaporator and are disposed of. Well pad separation systems typically consist of both a group separator and a test separator. The group separator splits produced fluids into liquid and gas streams at the well pad and can be either 3-phase, which splits the well effluent into free water, water oil emulsion, and gas streams, or 2-phase, just gas and liquid. The test separator is a smaller vessel which separates the produced fluids from a selected stream to determine the amount of oil produced, and this amount is reported to the Alberta Energy Regulator for the calculation of royalties owed. The test separator can be used to prorate a portion of the group production rate, and multi-phase flow meters are emerging technologies that seek to augment or replace test separators. We will now move on to equipment certification summary. In Canada, all products must be approved for use before being put into service. The Standards Council of Canada, the SCC, accredits several agencies to distribute certification labels for products. All agencies accredited by the SCC follow strict International Standard Organization standards in terms of quality, conflict of interest, and information security and management. These agencies are defined as certification bodies. Certification bodies use adopted codes and standards to evaluate products for certification. Certification is a federal process that ensures specified products are reviewed per an accepted standard. This regulatory process applies to the individual components. Its scopes progresses until it encompasses a configuration of components, which can be identified as a distinguishable product referred to as an appliance. Certification includes all aspects of the appliance, such as the electrical, documentation, fuel, pressure rating, and bilingual safety labeling. Any appliance or component that enters Canada bearing the marking of one of the accredited certification bodies is permitted for use in any jurisdiction in Canada. And note that certification bodies only attest to the safety of the product, not its function, unless that function is defined in the standard to which it is certified to. The route to certification depends on the number of units produced, whether it is greater or less than 300, and the appliance function. As a result, there are three methods to obtain certification of an appliance. There's standard certification, special certification, and special inspection. In standard certification, certification bodies operate at the point of manufacture. Certification bodies accredit original equipment manufacturers' production facilities for production runs exceeding 300 units yearly. This provides the original equipment manufacturer with the ability to affix their own compliance labeling showing that it is certified. In special certification, this is applied when some appliances lack a standard to which they can be certified or are not produced in the numbers required, 300, to warrant the accreditation of the original equipment manufacturer. In these cases, certification bodies have the option to perform special inspections on those appliances. These inspections are comprised of several safety standards pertaining to the appliance to assure it meets the minimum level of safety requirements. The appliance receives custom labeling denoting the various metrics used to approve the product. Special certification can be performed at the point of manufacture or the destination. In special inspection, the third option for the certification of appliances in Canada is through the Standard Council of Canada accredited organizations known as inspection bodies, which can perform special inspections of certain appliances on site. Dependent on their accreditation, inspection bodies can apply one specialized code for which no other standards applies, or inspect appliances produced in limited runs, which is defined as less than 300 units per year. Inspection bodies can review these appliances and components with an extremely limited scope. Little deviation from accredited standards is permitted in these cases. Inspection bodies do not allow for appliances comprised of non-Canadian certified components or for deviation from the certified purpose of those components. Inspection bodies operate under the direction of the local authority having jurisdiction, which is a provincial representative often referred to as the chief. In the province of Alberta, the Alberta Safety Codes Act is the overarching document that dictates how appliances are installed and operated. It delegates power of authority to several chiefs, depending on the discipline, and there are three primary authorities with jurisdiction. The Alberta Municipal Affairs, the AMA, which is responsible for the installation of plumbing, sewer, electrical, and fuel systems. The Alberta Boiler Safety Association, which administers Alberta's pressure equipment safety programs. And the Alberta Energy Regulator, which is responsible for public safety, interest, and the environment. To summarize, in a standard certification, the party approved to apply certification mark to the product is the original equipment manufacturer. Where the location of the certification takes place is the point of manufacture, and the requirements for certification are the appliance is approved to a standard and manufacturing methods are proven to produce a consistently compliant product. Examples of such equipment are control panels and valves, and the cost of certification is relatively high. It can be anywhere from Canadian $15,000 to $20,000 approximately, but after that point, all products are approved that the original manufacturer produces. The certification risk is low, as once a prototype is evaluated and certified, production and importation is largely assured. In special certification, location of certification is the point of manufacture or on location, and the party approved to apply the certification mark is a certification body. The appliance must meet a specific standard or a compilation of standards to cover the entirety of the product, and examples of certified equipment are boilers and specialty control panels. The cost of certification is lower than standard certification, as it is the inspection of one appliance, and the cost components include the evaluation of that product, travel to that product, and consideration of its unique nature. Certification risks are medium, as documentation review prior to inspection will often identify 80% of deficiencies, and other deficiencies found on site may require a repair and reinspection for approval. There are more avenues of certifications using numerous standards in this approach. In special inspection, the party approved to apply the certification mark is the inspection body, which occurs at the point of manufacture or on location. The appliance must meet a standard or compilation of standards, including any site-specific requirements incorporated into the inspection. And examples of such certified equipment are specialty processing equipment, fuel trains, and burner management systems. The cost of certification is lowest in this case, as it is the inspection of one product. And the cost components include the evaluation of the product, the consideration of its unique nature, travel, and upgrading it to Canadian requirements on site if required. The certification risk in this scenario is high, as other deficiencies found on site may require repair and reinspection for approval, and strict requirements that all components of a constructed appliance must be already approved for use. Examples of certified equipment used for standard certification include control panels and valves. The cost for these avenues of certification are high, as all products are approved once certification is obtained by the original equipment manufacturer. The risk of certification being granted is low, as once the prototype is evaluated and certified, production and importation in Canada is largely assured. In special certification, such equipment includes boilers and specialty control panels, for example. The cost of certification is lower than it is for standard certifications, as it is the inspection of one appliance. The risk of not obtaining certification is medium, as documentation review will identify 80% of deficiencies, and other deficiencies found on site may require repair and reinspection for approval. And in this case, there are more avenues of certification using numerous standards. Special inspection equipment may include specialty process equipment or fuel trains and burner management systems. And the cost of certification is the lowest compared to the other two avenues, as it is the valuation of one product. The certification risk, though, is high, as there are strict requirements that all components of a constructed appliance must be already approved for use in Canada. And so deficiencies found on site may require repair and reinspection for approval. In conclusion, the goal of this project was summarizing the equipment used in steam generation, de-oiling, and well pad separation systems in Alberta, as well as manufacturers of steam generation and de-oiling technology. Examining current challenges facing commercial steam generation equipment and emerging technologies, as well as providing a review of Canadian equipment certification processes. Additional topics for further evaluation include review of custom designs against applicable regulations, codes, and standards, and an in-depth evaluation of an appliance for de-oiling, water treatment, and/or steam generation, with a comparison to existing technologies used by oil and gas operating companies, for example, by examining technology, readiness levels, and capital expenditure costs. Thank you very much for your time. If you wish to contact myself or my coworker Dale Friesen or Brian Wegg, please feel free to call or send us an email via any of our information on this slide. Thank you.